Hello.
Hello, sir.
Hi. So, good. So, how are you all doing? I can see some more people are coming in. So did you guys get a chance to go over the videos?
Yes, sir.
Not the last one.
Not the last one. Yeah, I posted one last night, so that's fine. So that's okay. And what about the assignment? Did you go over them?
No, I was facing problem in question 1 part B.
Question 1, part B, you have a question.
Yeah, like I'm unable to start at all. How do I even start in that part? It's regarding 13 coins.
Right. Did you get these 14 coins?
I guess the 14 coins was pretty easy.
Then you should be able to do 13 coins also. It's basically same argument, just one more or two more extra steps.
Okay.
Yeah.
Sir,
Yeah.
there was a question in the first video from the first 10 natural numbers. If I took two big numbers randomly, the expected runtime of Euclidean algorithm.
The expected runtime of which one was it? I was saying.
To find the GCD using the
Find
Euclid's algorithm. So please discuss that one and what is the difference between binary search and the decision tree? I mean, decision difference between binary search and decision tree.
Okay. Binary search and decision tree. This is an important one. So I will just explain what the difference between binary search and decision tree. Yeah, for the randomized stuff, I would not do it right now. I will do it sometime next week. I will be kind of going over the randomized algorithms a little bit, and then I will talk about it. Okay.
Okay.
For this picking up two random points, random numbers. Yeah. Okay. So maybe I will just wait for another few minutes for people to come. In the meantime, whoever has any other questions can let me know so that I can.
Yes, sir. Related to, like, I have two questions. First is related to the second video. The decision tree, the way you arrived at the lower bound for the binary search with that depth argument, it was not not entirely clear. I think it was a little fast there. The last part of that video was a little
Okay, I will go
fast paced.
Fine, sure.
And the second part was related to the assignment, related to the presentation as to what is expected, like what kind of format should we follow, like should we give a pseudo code followed by a correctness of algorithm followed by an analysis of complexity, like what is expected.
Okay, see, yeah, I would say that you should write a pseudocode because almost all of the places that are there, except for the last question, the pseudocode is very simple. Okay.
Okay.
Except for the last question, pseudocode is pretty simple. So you should write a pseudocode. For the last question, it is fine if you, instead of writing a pseudocode, you can try to describe your algorithm in some other way. That's also fine. Okay. And you should technically give a proof of correctness and proof of time complexity. But see, this is the kind of a place where you have to use your judgment. I mean, if something is very simple, right? You should not spend one page to write a right. At the same time, you should also understand that there might be some places which are not obvious, and there you should explain that the correctness and. Okay. So I don't expect you to write details on every possible thing. Okay, but there is some amount of details you have to write, some of the explanation that you have to write. Okay, so you can look at the third video that I have posted. So there I have kind of given you how to write a formal proof of, or give a formal proof of, say, the correctness of binary search and all. Okay, and I mean, at least for the first assignment, I would prefer that you guys write some amount of details. Of course, as we go across the go over the courses one by one, go the lectures one by one, the problems will get more complicated. The algorithms will get more complicated, and in that case, some simple things like correctness of binary search will not be required any longer. We'll assume it almost as a black box or even some similar thing. Okay. But it should be that if somebody, for your purpose, you should know how to write. If I pin you down, if I say I ideally don't understand what you have written, you should be able to give me a formal proof. Okay.
Okay, sir.
And so for this particular assignment, for all but the last question, I think you should give a pseudocode and possibly some explanations with that. For the last assignment or last problem, also you need to give an exam, some explanation. But I will be a bit more relaxed on the writing part. So that problem, I think the technique, the algorithm design is much more complicated than anything. Oh, by the way, in that last question, in number 6, there is an open question. So you know what an open question is, right?
Yes, sir.
We don't have a solution to that, okay? And if you can find a solution to that, you get a new result. So don't break your head too much on that. But if you're interested for the challenge, go for it. Okay. Any more questions before I can start answering some of this stuff? So what I understood is I should kind of explain you the lower bound for binary search, say, using decision tree. I will kind of go over it once. And anything else? Hello? Hello?
Yes, sir.
Yeah.
Sir, please explain the difference between the binary search.
Yeah. That will come as a part of that explanation.
Okay.
Yeah. Any more? Anything else? Nothing? Okay. So good. So let me then go over this one. So by the way, can one of you keep your make one of you whose background noise is not too much can keep yourself unmute, because if I don't hear anything from you guys completely, I'm not understanding whether I'm connected or not. Hello?
Sir,
Yeah.
sir, I have a question.
Yeah, go ahead.
Sir, in general, how do we prove the lower bound things? Do we assume that there is a better algorithm with a better time complexity and try to prove a contradiction, or how we go over it? There could be many number of algorithms
Exactly.
which can.
Yeah. So see, that is a lower bound means that proves that if there exists prove that there cannot exist any algorithm, okay, that has a better time complexity. Lower bound is not saying that this particular algorithm cannot have a better time complexity. Lower bound says that no algorithm can have a better time complexity. Okay.
So how do we prove that in general?
Exactly. So this is a hard problem to ask. Okay, this is a hard question. So we will learn few techniques in the whole set of the course, but proving lower bound of, so lower bound is not of an algorithm. Okay, so lower bounds are therefore of a problem. So it's a lower bound of binary search. Binary search is the problem that we're talking about, not the algorithm. Okay. Fine. Or for lower bound of GCD, finding GCD, that can be a lower bound. Okay. Lower bound is not of the Euclid's algorithm. Lower bound of finding GCD. So similarly, so finding or proving lower bound of problems in general is a very hard problem. I mean, you will understand it by the end of the course that there are a lot of things we don't understand very well of lower bound. So there are some techniques. We will go over some of the techniques, but yeah, there is no thumb rule as such. So in the video, I kind of spoke about one particular rule, and that's about it, right? And then we will be going over some more such rules. Okay. Any questions before I jump into this explanation? Okay, let's do it. Is Shayantan or Chandrima there?
Yes, sir.
Yes, sir.
Can Chandru, can one of you keep, or maybe both of you, can you keep your microphones on so that I can hear some noise from your side?
Okay.
Okay, else, because otherwise I am really confused whether I'm connected to the internet or not.
Yes, sir.
Okay, good. So let me start sharing the screen. Can you see my screen?
Yes.
Okay. Okay, good. So now we will try to prove the lower bound for binary search. Okay, so here I must say that there were two parts. Okay, there was a binary search. Okay, binary search is you can say it's an algorithm, right? It's an algorithm that we talked about. But also I was actually using something, so let's call this one search be a problem. Okay. And what is the problem? The problem is that you are given an array, okay, A1 to AN, and you want B, and you want to check if B is in AI. Sorry, not that. Check that if there exists an I such that B equals to AI. Okay, so this is the problem, fine. And it is, when we talk about the lower bound, we would say that, so the lower bound is for the problem. Lower bound is for the problem. Meaning what we want to prove is that there doesn't exist any algorithm that solves the problem in less than log n steps. So let's put log n base 3 steps. Okay. Okay, is it clear? So this is what we want to prove. Now there is another thing that I am not told about. What does this algorithm mean? What does it mean by any algorithm? Okay, so here I am using some kind of a, so this means that, I mean that any algorithm, so this what I mean is that any algorithm that correctly solves the problem. Okay, problem for all A and B. Okay, so here is the problem, and I want, like, give me any algorithm that will take any A and B and will correctly solve it. It's very important. It has to correctly solve every bit of it. And such algorithm, I will say that it cannot use less than log n base 3 steps. And this is our theorem you can think of, okay? If you want to call this one, you can call this to be our lower bound theorem. Fine. Now it is important to note that in this whole theorem and problem that I have defined, there is no binary search. The binary search was one such algorithm that was solving this problem. My lower bound is for all problems, all algorithms. Okay. It is not just saying that binary search is, I'm not saying that this lower bound is for binary search. This lower bound is for all algorithms that solve the problem, which will also imply that lower bound is for binary search also, because binary search is one such algorithm. Okay, so this will answer the question that first person asked. That when we talk about lower bound, it is nothing to do with binary search. So binary search is not there. You could have come up with a completely crazy algorithm. I don't know what is that. Maybe the algorithm first goes and queries all the APs where P is a prime number and does something with that. I don't know. Maybe that's some very weird way of doing it, right? And I have really no idea what your algorithm does. Okay, so this is the hard part. That the algorithm can be anything. It is not structured. I have no pseudocode of the algorithm known. It just does it. And all that I'm guaranteed, all that I know of the algorithm is this part, that the algorithm solves it correctly on any input A, any input of array A and number P. Okay. So binary search goes out of the window. Now, how do you handle, or how do you prove anything which is holds for all algorithms or all things? Okay. So one thing that you kind of possibly know is that, so this maybe I will write it as a proof. Okay. That one way of doing it is that we can try to abstractify this algorithm. So these algorithms, what does an algorithm do? Okay, I don't know what that algorithm is, but what does any algorithm do? It will first take, and basically what I will do here now is just to make it more easier, I will assume that it's deterministic, meaning there is no randomization here. Okay, if you don't understand what a randomization is in an algorithm, don't worry. Okay, so what it means is that the algorithm, what it will do next step, this next step of the algorithm is purely determined by whatever it has done so far and whatever answers it has got for its query. Okay. So first thing is that this algorithm, and since we are talking about numbers and all, so it is going to compare a particular number B, this number B, with a particular, so I kind of wrote it, with a particular AI, right? So this is the question that you can ask. The first question that one can ask is that, is B less than or equal to AI, greater than or equal to AI, or AI? I don't know what their I is. Now, this is the first question. First question you can ask. Again, I don't know what I is. I can be anywhere. Now, it can get three answers, right? One of the answers is that oh, B is less than. One says that oh, B is more than. And one says that B is equal to. Now, that algorithm, if it gets B is less than, what happens? It now decides to ask another question. Correct? And in that case, it would make another question. What kind of question is this? Is that it would be possibly asked something like, is B less than or equal to AJ? Now that J, what is this J? Note that this J can be a function of Okay, in some sense, it's a function that is dependent on what it has asked initially, I. It can be a function of b, and it can be a function of the fact that I have got a less than symbol. When it comes here, it can ask something similar, but this can be equals to k. I don't know. Maybe I and j and k are same. That also is possible, but maybe it is different. And similarly, it can ask p is less than or equal to al. Fine. Now again, at this point, it can get three different answers: less than, equal to, greater than. Say it gets less than. What does it do now? If it does now, then it will again ask something like, if a bigger than or equal to, say, a, I will run out of index very soon, say m. What is this m dependent on? So m is some function, so let me type g, that is dependent on everything that it has seen so far. So it is dependent on I, it depends on b, it depends on the fact that this is on the less than in the first round, and also depends on the fact that it is less than in the second round also. Right? Similarly, here, say example, if I ask if a less than p, so this p can be a function of g prime of I, b, less than and greater than. So this is how the function happens. Okay, this is what you can sometimes call adaptive algorithm, meaning the next query you do is depending on the answers that you have got. This is what any algorithm will do. What I don't know is, of course, that what are these functions, what are this function f, what is this I, what is this g, what is g prime. I have no idea what the function, what the algorithm is doing in its head. But the algorithm does this always, right? So in other words, it can, for any answer, maybe if it comes here, say it is equal to, maybe the algorithm will stop right now. Maybe it will, in that case, it will not even ask any questions here. Maybe the algorithm stops here. No, now I've got it, I'll output the answer. Maybe it will output something else. Maybe in this case, it will kind of go into 3 more stops. So what happens is that if you forget this whole I, J kind of things, all the questions, what is happening is that the algorithm first makes a query, then depending on its 3 answers, it makes another set of queries. Depending on the answers of the previous ones, like, so in this case, this we can call it as the root, which is this root. It will make again 3 queries, 1, 2, 3. Here maybe it doesn't have queries, maybe here it makes queries. Okay, I don't know what it happens, but it can continue like this, right? So this is, maybe it will make 2 queries, maybe something, I don't know what, right? So this the algorithm's computation is basically captured in this tree format. Okay, this is called the decision tree. Decision tree is of our algorithm, or any algorithm rather. Okay, so we can write a decision tree of binary search. I can write a decision tree of any algorithm that we have given you. The tree structure might be different for different algorithms, but the tree structure exists. Okay, note that you can say, oh, why is it a tree? Why can't I land up from here to here? I mean, you are right. Maybe if you can ask the same questions possibly, right? But this will be different because you are taking a different path, right? What you end up doing it is basically depending on whatever you have seen so far, you will make a question. So maybe this question and this question might be identically same. That is possible. But this question comes from the fact that after this is the answers we have got, I have come asked. And this question comes from the fact that I have answered got this kind of answers, and accordingly I have asked this question. So I'm not saying these nodes ask different set of questions. Some of the nodes might ask the same set of questions. Okay, and there are many of the questions might ask some questions. But this is how it will kind of spread. It might be different also, right? Now, so this is the decision tree. Now it is important to know what happens at the when the decision tree stops. So when after a lot of hard work, it finally comes up to this state and it stops here. What does it mean? It stops, right? What does it mean that it stops? Maybe the actual decision tree that we have constructed is something like this. So this is the actual decision tree, whole computation tree of this. That means at every end, given the algorithm is supposed to output correctly for every bit. That means once it comes to one of these endpoints, the leaves, right? It is supposed to output something that is either B is in S, B is in A, or B doesn't exist in A. And in fact, say if B is in A, I want to output that B is equal to A of I. So means I have, so the algorithm will compute, keep on going, the red color or purple color. So I go on this path, I ask this question, I get this question, and I come here, and at the, oh, okay, good. So now that means B is equals to A of 5. That is the output that you can have. Or you could have gone here, here, and here, and then, oh, no, B is not in A. Or maybe you could have gone here, here, and here. And finally, you have only one answer to give, right? And B is equals to A of say 7. Right? So that means every leaf should have an output. Right? What are the possible outputs? Let's write down what are the possible outputs. Nothing but either B equals to A of 1, or B equals to A of 2, or okay, or B equals to A of 3, and so on and so forth, right? Or B equals to A of n, or B is not in. So there are all total n plus 1 outputs that can be given in the leaf. And now think of it. This algorithm is supposed to work for all A and all B, right? This algorithm. So if it happens that I have given you a graph, I've given you an algorithm that outputs everything, but in none of the leaves, A of B equals to A of 1 is there. Okay, so let's say, let's write it here. Can it be that B equals to A of 1 is not in any leaf? Is it possible? So that means, see what? That means that the algorithm at no point of time will output that B is equal to A of leaf, A of 1. But I could have given you an A where the B is actually equals to A of 1. In that case, the right answer would have been B equals to A of 1. But the algorithm never outputs that. So that means the algorithm cannot be right. So in other words, so this is not possible, okay? In other words, this set of questions, this set of n plus 1 answers should be there in all the leaves. Okay, so let me, I mean, maybe it is possible that, it is very much possible that there will be 2 leaves which output the same thing. That is not what I am worried about. But I am saying that every output must be there in at least one leaf. Right? So in other words, every output answer. Okay, so these are the output answers. Okay? These are the output. Is or must be present in at least one leaf, right? So what does it mean? It means that the number of leaves must be bigger than n minus 1. Now look at it. This is actually not a binary tree, it's a trinary tree, right? It's a three-way tree, right?
Yeah.
So in a three-way tree, this is something I'm not saying it, I'm not proving it. You guys go and find out or prove it. That it means that the depth of the decision tree must be bigger than log to the base 3 of n plus. Okay. And what is the depth? Depth is the longest path from the root to the leaf. So in this case particularly, this is a 1, 2, 3, 4. So this is the depth 4 tree. Okay.
Yes.
So what does the depth 4 tree means? It means that it is possible that there exists a weird answer, weird A and B, for which the tree will have to go down this path, right? And it is a 4 depth, 4 paths, 4 length path. So this is mean depth 4 means 4 length path, which means that the worst case runtime is 4. Right? The depth kind of computes the worst case runtime. Right? It doesn't mean that there will be no path that will, I mean, there will be very well some path that lands up in one depth. But that's not the case. I'm working about worst case runtime. Right? So this implies therefore that the worst case runtime of any algorithm, and then here algorithm I really should make it into red or something. It is any algorithm that is correct for binary search for the search problem and so on, right? Must be bigger than log n plus 1 base. So is it clear, this one? So of course you will say that, oh, this is better than binary search. In binary search, it was log n plus 1 base 2, and here it is log n plus 1 base 3, which is lower. You're completely right. I have managed to only prove a lower bound of log n plus 1 base 3, while I've given you an algorithm of log n plus 1 base 2. But as I will explain maybe after some time, just now only, in this lecture class only, in algorithms, most of the time, we are not too much worried about the constant. Since we work on the asymptotics, so log n plus 1 base 3 is nothing but, right? I mean, this is something all you know, right? N plus 1 base 2 into log 2 base 3. And log 2 base 3 is a constant. It is just a constant multiple of log n base 2. And that's
Sir,
what, yeah, go ahead.
sir, can you please explain the last statement once more, the worst case one?
Okay. Okay. So what does this tree means? Right? So this tree means that I can give you an A, okay,
Yeah.
okay, and I will keep on answering exactly. I mean, so that means that there is an A where and a B. So there exists an A and a B. Here. Yeah. So there exists an A and a B such that you will be getting this set of answers. The first one you will get this answer, second one you get this answer, third one you will get this answer, fourth one you will get this answer.
Yes.
Right? And then finally the algorithm outputs something. Right?
Okay.
So that means there exists an A and B for which I will make the algorithm ask 1, 2, 3, and 4 questions.
Right.
Right?
Hmm.
So that means there is 4 different steps of the algorithm, 4 comparisons that the algorithm has to make. Right?
Okay.
So if there is the depth of it is some k, if depth or d, okay. So if I have a decision tree of depth d, that means that the worst case runtime must be bigger than d. So worst case runtime is what? It's that, I mean, think of it. So we talking about in adversarial methods. Okay, adversarial meaning is that you have given me an algorithm, and I am your adversary. What I will do is that I will try to give you the worst A and B for your algorithm, which will make your algorithm run for the longest.
Right.
And that is the worst case runtime. Right?
Okay.
Time for which your algorithm will run in the worst setting is the worst case runtime of an algorithm. So here I can fix this A and B in such a way that I will make you make 4 steps, 4 comparisons.
Okay.
So the worst case runtime of your algorithm has to be more than or equal to 10.
Right.
Right? And this is exactly.
Thank you, sir.
Sir,
Yeah.
can you please explain the statement that every output should be present in at least one leaf?
Okay, good. Okay. Can you think about, okay, see, I can give you any A and any B, okay, right? Your algorithm is supposed to work for any A and any B. What does it mean? That if I give you an algorithm that, so I can give you I can put a B anywhere in the A, right? I mean, I can have a A by putting, okay, you pick your favorite position. Okay, oh, okay, my favorite position is a 70. I will put a B here and complete this sorted array accordingly. I can do that, right? I mean, so slightly less than B minus 1, B minus 1, B minus 1, some kind of stuff like that. Right, I could have done that. Right? So I can always produce an A and a B such that B is in whatever position you want, or I want, or an adversary wants. Fine. Now, imagine that your algorithm is such that it never outputs this statement that A is in B. It never outputs. B is equals to A of 1. It never outputs. Is it possible? Is it possible that your algorithm under any input A and B will output A is equals to A of 1? So I can do is that I can produce an A where I place B in the first bit and everything else is not B, something else, I don't care. In that case, your algorithm will be forced to, right, answer, if it has to actually answer the right thing, that B is equals to A of 1. Right. So it cannot be that your algorithm never outputs B equals to A of 1. Similarly, you can say that your algorithm can never output B equals to A of 2, and so on. So that means your algorithm at some point of time for some input must output B equals to A of I, B equals to A of I, AI. And this decision tree, by the way, is nothing to do with A or B. Remember, I have never written A or B anywhere. The decision tree is what happens after you get this response. You will be asking things like B, which is not known, it's a parameter in some sense, is B less than or equal to, where is it here? I'm going to ask these questions, right? Now here, don't fix a B. B is a variable in some sense. That is the input. And A is also a variable. So the only thing that your algorithm has fixed are these indices and the functions. So the B's are always variables for the input because I can change the B in whatever way I want. So this decision tree is how it will behave in general, this algorithm. It is not for any particular B and A, right? So this decision tree or this algorithm must at some point of time output A, B equals to A of I for all. And that is it.
Sir,
Yeah,
the decision tree is for a particular algorithm, right?
yes.
So how did you conclude that log n plus 1 is the worst case runtime of any algorithm?
So that's what, say, if given any algorithm, if I say that your worst case runtime has to be more than log n plus 1, then what does it mean?
That means that log n plus 1 is the worst case runtime of any algorithm.
Right?
But how do you prove that there does not exist any algorithm?
So this is what it proves. I took any algorithm, okay? Give me your algorithm. You gave me an algorithm. I produced a decision tree out of it. Okay? The decision is based on the algorithm. Then I told that, see, this algorithm should have they should have one property, namely all these answers must be there in the leaves of your decision tree. So what I did is the following. So this is exactly what. Maybe I should write it again. Okay. So give an algorithm A. From that, I will produce a decision tree, which such that it has two properties. Number one, actually this has one property. Let's say such that. No, let's two properties. Such that first of all, the worst case running time is the depth of the tree, and two, that it's a property of a tree. Okay, any algorithm will have that the number of leaves must be more than n plus 1. So you give me any algorithm, I created a decision tree, right? I mean, any algorithm has a decision tree, and that decision tree has the number of leaves is at least n plus 1. So this is what I argued here, right? Because
Yes.
every decision tree must have this set of things in its leaves, right? So what does it mean? From these two facts, what do I have? Actually, from this fact, what I have is that means that the decision tree has depth more than log n plus 1 base 3, and which means that because of this number one, that the algorithm A has worst case runtime. Of log n plus 1. Is it clear?
Yes, sir.
I mean, I can repeat this one again and again. That's no problem with me.
Sir, I had a question.
Yeah, go ahead.
So our array has n elements or n plus 1 elements?
Okay, it is n elements. We are using n elements.
In that case, shouldn't the number of leaves be greater than or equal to n rather than n plus 1?
Then n plus 1 because of the last one is that also it is possible that B is not in here, right? That's also an answer.
Oh, right. Okay.
See, this is just one way of attacking this whole thing. Okay, there are, I mean, decision tree is not necessarily the only way, because analyzing it through decision trees sometimes become very tough. for many steps.
Sir,
Yeah.
we are assuming that at each step we are comparing B with some element having three results.
I mean, if you compare it, how many results will you get?
No, but I mean, we shouldn't the bound can be improved by the fact that whenever we get an equality, the tree does not grow further.
That is fine. That's what I told. This decision tree doesn't have to continue, right? This decision tree, many of them are stopping over here. Okay, I'm not saying that tree is a complete tree. The tree can be truncated. See, I'm not interested in the average depth of a tree. I'm only worried about the maximum depth of a tree. And this statement that this one, right? If the number of leaves is, so this statement, right? That number of leaves is bigger than n plus 1 implies the depth of a tree. Maybe if you should write it worst on the largest depth, I don't know. It is called the depth only, but just to kind of clear your doubt, let's call it the longest depth. The longest depth of distance must be log n plus 1. This holds for any tree, whether it is truncated or not, halfway or not. So it doesn't have to continue. If the algorithm thinks that, oh, I have got an equality, I will stop, that's perfectly fine.
No,
In fact,
but
it might stop even earlier, for example, you understand that, even with a non-equality. For example, it might compare B with the last element, and the answer is no, B is bigger than the last element. The algorithm might stop right there. Oh no, now therefore B is not, you don't need to proceed. B is not there. So truncation might happen at various levels. Yeah, so go ahead.
but in this case, equality holds if the number of leaves, the branches increase by power of 3 in each step.
If branches increase by a power of less than 3 in each step, then the depth will be even longer.
Yes.
Yes. So in that case, what will be the lower bound? Lower bound will go up.
Yes.
Yeah. So I am not saying that this is the A. I am saying that this is what is there. I am just giving you a lower bound. I am saying that you see, okay. I mean, if I have a tree, right, where every step can have at most, okay, at most. So every node has less than or equal to 3 childs. I hope they, so I mean, I'm actually assuming that you are very comfortable with trees and all. That
Yes,
is
sir.
right? Okay, good. So every node has less than or equal to 3 childs. Okay. It can have 0 child also. It can have 1 child. It can have 2 child. It might not have. Might have 3 child. Okay. Then, and what I am guaranteed is that it goes up like this. Maybe some part it is truncated and all. I don't care. But the number of leaves meaning not the last one, okay? The leaves are the ones, what are the leaves? Okay, so a node is a leaf.
If it is a degree 1 node.
If it is let's think of it going downwards, okay? It's kind of a directed thing, okay? If it has no child, okay? It has a parent but no child. This is the root, okay? The root, it goes down at, so the number of leaves is bigger than or equal to n plus 1. And these are the only two facts that I have. Every node has less than or equal to 3 child, and a number of leaves is more than equal to n plus 1. Then the depth. This is a fact. Okay, this is a I don't know what to say. Let's call it a theorem. I am not proving it. You guys prove it. Depth must be bigger than log 3 base n plus 1. It might be way bigger. I completely agree. But this inequality will still hold. I am interested only in the lower bound of the depth. I'm not saying that all trees of this form have depth in log n plus 1.
Sir, sir,
Yeah.
sir. Here, for each question, I have 3 answers.
Yeah.
Equal.
At
Less.
most. Yeah. Yeah. Right. Fine. Go ahead.
I am saying that for each question,
You have 3
in a particular step, I have 3 answers: less than, greater than, and equal.
Right.
But if some algorithm is such that there is more than 3 answers, I don't know. But if such an algorithm exists,
Yeah.
then it will be log base more than 3.
Right.
But then that
Then-
will be less than that.
Then
base.
again, if it is a constant, it doesn't matter for us. If it is a non-constant, it might be different.
No, I am not saying the order, but the lower bound.
I mean, for this problem or for a completely different problem?
Actually,
for this problem, okay, when you have a variable and this one, so let's look at it that what are the comparisons that we have done.
Okay, for this problem, we cannot have less than, greater than, and equal, and nothing else.
Nothing else. So
Okay,
this
okay,
for general problem, I can agree something can happen, weird things can happen.
Yeah.
But for this particular problem of search problem, you can have at most 3 things. Yeah.
Is the lower bound we obtained here?
Yeah.
It's for any algorithm. Means in this kind of problem, we can't avoid the comparison. Suppose there is a algorithm which kind of
very good. I was expecting this question from someone, and it is right. So I have actually assumed that all these algorithms that we're talking about are comparison-based algorithms.
So basically means we need one common property from like.
It is a, I mean, like this B. I mean, there is no structure on the inputs of A. Okay. If you say that the structure of the inputs of A is general, okay. In that case, all that you can hope for is a comparison. Okay. Think of them as abstract objects. It's a well-ordered set. That's all. A total ordered set. That's it. You have nothing else. Okay.
Yes, sir.
Instead of the numbers, think of it as a total ordered set. And then what can you do? Okay.
Sir, can you please repeat his question?
Okay. So here I was assuming that at every point of time you are just comparing one element with another element. See, maybe you can have an algorithm that do some much more crazy stuff. For example, you can look at the ith bit of B and some 10th bit of AJ and do some kind of stuff and some kind of stuff like that, right? So here, problem is that can be done. We will see some algorithms where it can do something nice, not for the searching problem, but for other things, where the structure of the numbers, okay, can be very useful. You can do some nice stuff. For example, if I had guaranteed you, for example, that the A's and B's, okay, are either zeros and ones, and the values that are stored in A's are just either 0 or 1. Okay, and B is also a 0 and 1. Then you can do much better. Okay, possibly you can do much better. So, but what we told here is that the whole thing was what is called a comparison-based algorithm. So if you have this element, which you have called the numbers here, forget the numbers. Instead of them, they are just elements of a total ordered set. In that case, all you can do is compare. That thing is, you can take 2 elements and compare. And according to them, that you make a decision. Right? So then this algorithm is lower bound holds. So in some sense, you are right that we have just given you a lower bound for comparison based algorithm.
Sir, please explain this once more.
Okay. So see, I kind of assumed already in the beginning when I was drawing this one that every element, every time I am making questions like this, right? Now, is that guaranteed that I'm going to have to make questions like this? What happens if you can ask that is b less than the square root of ai times aj? This is a valid question to ask, right? I mean, you could have asked this question. Is b less than or equal to ai times aj? Or some kind of weird things like that. Okay? But or say what is the ith, what is the 10th bit of, or what is the say first bit of, what is the first bit of yeah, something, I mean b times ai. I don't know, I mean, like some very weird things could have been asked, right? So these are valid questions that an algorithm can ask. Who stops us from doing that, right? And then, I mean, then you might be able to produce something slightly more interesting.
Sir,
Yeah.
can you please explain, like the lower bound, like the worst case scenario, which is there? Can you please tell that there should be an algorithm such that that worst case scenario is in fact attained? For example, in our case, I don't think there would be an algorithm which shows both equal to ai and b not belongs to a simultaneously.
No, it cannot, of course. I don't, that is not required. But okay, so again, it's not simultaneously, it doesn't have to show. See, okay, maybe this is something weird. So, see, this is a decision tree of the whole algorithm, okay? It doesn't mean that one run, what is the run of an algorithm? A run of an algorithm is, so this is a very abstract structure. There's no run, there's no A and B. If you remember that this is what I have told you, right? You can say a B is a variable, A is a variable. And every time you have this I which is fixed, then you have a function that depends upon these three things. Again, here b is the variable, and this number less than is something that we know what is coming out, right? So this decision tree is supposed to work for everywhere. Now, what does a run of an algorithm mean? A run of an algorithm means that now you fix a b and a a. Okay. Now, once you fix a b and a a, for that fix a b and a a, you will go down some path. Say you say, oh, okay, for this bit, maybe I am getting this path. Then I will see this path. Okay, so I will output. So a run of an algorithm, a single run of an algorithm will only produce one leaf. Okay. So a run of an algorithm will always produce one leaf. No doubt about that. But the issue is that there exists another B and the A that would take you to a different path. There will be another algorithm fixing of B and A that will take to completely different path. Right? So every run of an algorithm will produce you one leaf. But the issue is that,
sir, then I think it is better to say that a decision tree is related to a problem than to an algorithm. Like earlier, someone said that a decision tree exists in every algorithm.
No. Decision tree is related to an algorithm. See, the algorithm, what does an algorithm mean? I mean, decision tree is for the algorithm, not a run of an algorithm. Algorithm is algorithm has an input and the output. You have written codes, right? You have written C code, C programs, right? You compile it and you produce that a GCC version and whatever stuff like that. That's an algorithm. That algorithm, if you click it, it has nothing. It possibly just shuts down and says that, please give me an input, please give me an input. When you give that input, it then computes the stuff and produces some value. Okay.
But the decision tree is taking into account every possible algorithm, I guess. Like you told, every possible algorithm can be.
No. Okay. See. So a decision tree is like fix an algorithm. Okay. Okay. So let's do this following. Okay. Here is the first person. First algo for binary search. Okay. What it does is that it first compares B with the last element. Okay. Then it compares B with the, if it is less than, then it compares B with the last minus one element. Okay. If it is equal, it stops. If it is more than, it also stops. This is no, meaning not possible, and this is B is equals to AI. Then I have the next one. If it is less than, again, it compares B is less than or equal to A. Hello, can you hear me now?
Yes.
Okay.
Yes, sir. Yes, sir.
Share my screen. Okay. Sorry. So let me give you this. Let me just give you two examples. Okay. So here are this first algorithm. Okay. I have two algorithms. First algorithm takes B and compares it with the last element. Hello.
Yes, sir.
Yes, sir. B compared to last element. If it is less than, then it compares B with the last but one element. Again, if it is less than, it compares it with last but two elements, and so on. It continues like that, right? And for everywhere, if you get the any other two things, you get your algorithm stops, right? Note that this is a valid algorithm. It gives you the right answer. Similar, but on the other hand, I could have also given you the other stuff where the binary search, right? So B is less than or equal to A n by 2, right? And if it is now bigger, then I will go to B A 3n by 4. If it is equal, I will output, and here I will output say B is less than or equal to A n by 4. So this is a standard binary search algorithm, which is the second algorithm. And here is the first algorithm. Okay. Are you guys convinced that these two algorithms are valid algorithms for the search problem?
Yes, sir.
Fine. Now, what are the decision trees? Let's see. Is this decision tree, does this decision tree look similar? See, here it will have, right? This decision tree is a kind of narrow looking decision tree. It will be a very narrow decision tree. This is the decision tree that will be kind of slightly more spread out. Hello? Hello? Yeah.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Okay. Fine. So you have these two decision trees with completely different structure. And this is what I mean. It doesn't mean that at the end of the day, okay, and more importantly, for both of this stuff, there will be, so here it will be writing as, okay, the first one is that B is equals to an, this will be B equals to an minus 1, and so on, right? And there will be no in all of them. And here also it will be B equals to an over here, this is B is an by 2, and so on and so forth. So there is two different algorithms, right? And both of them algorithms will have the property that b equals to ai is there in the, for all I, that will be there in the leaves. And once I start a particular instance, when I give a particular a and a b, okay, then it will take some particular route. Maybe it will take this route and output something. And here it might go for a different route completely. It might go for these, and continue, and then. Okay, so the decision trees are for a particular algorithm. Every algorithm has a decision tree. The decision trees can have different structures. But all that I care about is the properties of the decision tree. So every decision tree for the search problem will have the property that there will be leaves, one leaf at least for b is equals to ai. Okay, so that means the total number of leaves on each of the decision tree has to be more than n plus 1. Is this clear? Slightly more clear? Hello?
Yes, sir.
Yes, sir.
Okay.
Sir,
Yeah.
what Tathagata said that there we can use something else than comparison in the algorithms, but whether we do any other thing, we still will get. I mean, the order cannot be better than log n plus 1.
Exactly. In this particular setting, that is what will come. I was going to say that for this particular binary search kind of stuff, okay, I let you guys go and think and prove it that you cannot get anything better than log of n plus 1. But if I ask you that I don't care about which index you are output, what index is b, but all I care about is b in a or not, then something else could have been done.
Sir,
What do you mean by index? I mean,
So here we are saying that at the end, you should output is b in ai, is b is equal to ai, right?
or
But maybe I don't care about whether b is where is b located. All I care is a yes no answer. Is b in a or is b is not in? Then I mean neither did I whatever I explained will work. This will work for comparison based algorithm. You have to prove it that even for that you can get a lower bound of log n. And for other algorithms also you have to kind of come up with a more cleverer trick.
Sir, I have a question that is, say for an algorithm like finding the maximum element in an unsorted array.
Yeah.
Here, like you had a question that its maximum lower bound should be n minus 1. Matlab it would need at least n minus 1 comparisons to arrive.
Right.
So I'm like finding it difficult to construct a decision tree and arriving at a depth because like in this case there is a log n structure.
As I told you, lower bounds is a very tricky object. Okay, I can give you only one hint. That lower bound is not using decision tree. Think about it. It's an easy lower bound. It is an easy lower bound, but not using decision tree. Okay. Lower bound.
Sir, I have a question.
Yeah, go ahead. Hello.
Hello.
Yeah.
Yes,
Go
sir.
ahead.
Sir, the lower bound problem that we formulated earlier, formally, there does not exist any algorithm that solves the problem in less than log n to the base 3 steps.
Right.
So, and by any algorithm, we meant that any algorithm that correctly solves the problem for all A, for all A and B, right?
Yeah.
So, sir, does the binary search even come in this realm? Because it might not. It needs a sorted array, right?
No. I meant a sorted array. The algorithm that we're talking about, I meant a sorted array. All over the place. So sorry, maybe I missed it there.
Yeah. In the previous
I meant you sorted. Okay, if it is not sorted, you can get an even better lower bound. Yeah.
Sir?
You mean sorted, yeah.
So in the previous doubt, you said something about the means one trick or something about n minus one.
Yes.
Then finding the maximum of an array. Can you repeat that? I didn't hear it.
So that's the question about this n, proving that n minus 1 comparisons is required for finding the maximum. Okay, that's a lower bound problem. Okay,
Yeah.
but the hint is that, or I mean, you can convince yourself also to some level that decision tree is not the technique to go to that lower bound. I'm not saying the decision tree is the only technique. There are lots and lots of techniques. Okay.
Yes, I get it.
So there is a pretty simple technique and a very cute technique also. Think about it. Okay. So see, this is actually the fun about algorithms. This is something that possibly you have never seen in your any other courses till now. It is about hardness of something. That something cannot be done. We can give formal proofs of that. Okay. I mean, there is a way of giving formal proofs of some of it. I mean, so this is something that I think you will get some much more interesting results, I will tell you, particularly towards the end of this course. So lower bound is a very important part of the algorithm and possibly the most fun part. Okay, so decision tree is one way. Okay, for example, if this one was not sorted, okay, if this array was not sorted, then the lower bound is n minus 1 or n actually. Okay, decision tree will not give you that. Decision tree will only say that you need log n depth. Okay. Okay. Any more questions?
Yes, sir. I have a question. So at the end of this discussion, when we are talking about binary search, we conclude. So what is the conclusion? The conclusion is that it is for searching in a sorted array.
Yeah.
It is it is one of the best that you can get, right? Because it performs. So
Yeah.
that was the conclusion, right?
Yeah.
So based on this, I have a question. Like based on, so let us say I have two algorithms, algorithm 1 and algorithm 2.
Right.
And algorithm 1 performs in the worst case, like let's say order n,
Right.
of order n.
Right.
And algorithm 2 performs in the worst case, let's say order log n. Right.
Yeah.
So and we say, okay, so log n, we take the second algorithm to be a better one, but the mathematical formulation for upper bounds just says that in the asymptotic case it is bounded by n and one is bounded by some constant times log n, right?
Right.
The run times.
Right.
So does that necessarily imply that algorithm
No, of
2
course
will
not.
be
So,
better?
no. See, when we say better here, okay, I mean, most of the time it will be kind of implicit, but thing is that we will be talking about mostly worst case, okay, but then there are analyses that are done for average case, okay. We will see some examples very soon in the next class or next class, where the average case algorithms are considered to be better, even though they have worst case algorithm, worst case runtime. There are even other things. Okay. So when I told that the binary search is the best, I meant the binary search is the best for the worst case runtime. Okay. I did not actually mean that binary search is best in the average case runtime. Okay. And again, when I told it best, I meant in the asymptotic sense where we are not too much worried about, and we are interested in the function of n, not the constant. Okay, so whatever the binary search pseudocode was written up, I'm sure there are other tricks that we can shave off a factor of 2 or 3 somewhere. Okay, and instead of log n, maybe you can get some log, yeah, like here, right? So that is all those things are possible to do some kind of crazy argument and all. Fine. So whenever, so it is, I mean, coming up with a kind of flat out statement that this algorithm is better than that algorithm is kind of, I mean, not right under any perspective. Okay, I mean, it is You cannot compare two human beings and say that this person is better than the other person, right? Similarly, I mean, on a particular parameter, this is better than that. That's all I can say. On worst case runtime, this algorithm goes better than that algorithm. On average case runtime, maybe some algorithm is better than some. On a space complexity, this algorithm might be better than that algorithm. There are lots of other structures. We will come to that very soon. In the next class, or next class, we will be talking about sorting, which has much more flavor of that. But we have a lot more algorithms to compare, and we will compare which is better. And you will see that, I mean, it's very hard to kind of argue that, but which is the best algorithm. But from a mathematical point of view, we are only worried about a particular complexity issue. Okay. Any more questions?
So in the second assignment question,
Yeah.
it's you asked us to prove that Pn/2 comparisons suffice to find both the smallest and largest from some n real numbers. So it's not a lower bound problem, right? We just need to give an algorithm
Yes,
which.
that's not a problem. Yeah. That's not a problem.
Yeah, and just confirming the fourth problem, we can't use the square root function, right? Obviously.
I mean, what is square root function? You can whether you can produce a square root. Yeah, that is. I mean, you can. Okay, let's say that you can apply a square root function and yeah, you can ask a square root function. How does it matter? But that does solve it immediately. Yeah.
Yes, then it will take just order of one step.
Why?
No, that depends on the comparison of floating comparisons. Or,
No. So what was the question there? I forgot actually the question there.
To check
perfect number.
If a number is perfect square or not.
If a number
is perfect square or not.
Is a perfect square or not? Okay, so that means okay. No, so then you will have to get this exact number, right? Yeah. No. You don't have the ability to produce the square root for a. So you can get the square root thing, but you will not get a floating point. You get only the maybe the box function.
Sir.
Yeah.
In questions 3 and 5, it just says to design an efficient algorithm.
Yeah.
So,
okay,
like,
so
what
this
time
kind of questions I will be asking continuously, and you will get it also. Okay. So, given an efficient algorithm possibly means that there is a very brute force algorithm in some sense. Okay, meaning kind of an order n algorithm or something like that. Okay, sometimes even worse than that. But the goal is to reduce the worst case running time. So, can you come up with another algorithm which is a slightly better? Okay, so here I have kind of left it. So this is how we solve problems in our research. That we have a problem and we have to come up with the efficient algorithm. Now, that is the bad algorithm, but question is that can you push it down? Okay, so we don't know what the target thing is. We don't know how
to show both the bad and good algorithm. Means in the paper.
No, not necessarily. But I mean, like this helps me that if somebody gives a bad algorithm, also you get some marks. Okay. Which at least this is some algorithm. And then if somebody produces a slightly more efficient algorithm, you get some marks. If somebody produces an even better algorithm, they get some more marks. This is basically how it works. Okay. I mean, there is no target in some sense. I mean, there is a target which we don't know. So the best thing that one can do in this kind of situation is produce an algorithm, okay, with a particular worst case running time, and also produce a equivalent lower bound, and say that, oh, so this is tight. At least asymptotically it is tight. That is kind of the optimal result that you can perform. Okay. So this is slightly open-ended question to some level. I agree. But you should get used to this kind of questions. Okay. Any more? Hello. Am I there? Yeah.
No, sir.
It's a very weird thing. I don't understand when I am here and when I'm not here.
Yeah, you are connected.
Yes.
You're here.
Yeah. Okay, so I wanted to talk something about the asymptotic notations, but that I could not do because we are discussing some more important stuff. But I suggest that you guys read up the asymptotic notations from your from the lecture notes that has been uploaded actually. Laszlo Baba is in the lecture notes that has been uploaded. Please go over it. It's pretty well written, very cleanly written, and all. And mm, uh, so yeah, so let me ask you guys the question. Do you guys want another class on Saturday or not? Hello. Okay. So with such a quiet audience, I assume that you are not that interested here, maybe, which is fine. I mean, I also don't want to really push you too hard on this online classes. So instead, what I will do is that, I mean, okay, you have an assignment anyway to submit on Tuesday. We are anyway going to meet on Tuesday. If people are interested, okay, please drop us a message or something in the classroom and something. We will try to organize something. Either it will be me taking a office hour class or maybe one of the TAs taking an office hour class. Okay, but they kind of explain a little bit on the asymptotic notations particularly, or other all this kind of binary research, sorry, the decision tree stuff. So yeah, so please, if you guys want one more class explaining, whether it's from me or from somebody else on Saturday, please drop a message in the classroom. Okay, and in that case we will organize one. And do it by tonight only, so that we can prepare accordingly. Fine.
Sir, actually, sir,
Yeah.
I have not solved all the problems of assignment, but done some of them and have seen the two videos.
Yeah.
Actually, the notes, what have you sent in email,
Yeah.
that is left, and also you have sent another video. You
Right.
have to I have
Right.
now just known,
Yeah.
and many things are left. So actually, I have not completed in this less than 48 hours. So this
Okay, you
that
want
will
a
be
break?
better if
Yeah, it will be better if. No, we will
if
not
you
be
go
covering.
if
We will not
little
be.
slow.
Oh, a little slower. Okay, sure.
I mean, this assignment, these 3 videos, and that note, that is too much for just for 2 3 days.
No, that is too much of procedure. I completely agree. But anyway, the first video was kind of pretty simple. So in that respect, that was not something you just observe, watch it once, and that's it. The second video, hello, yeah. The second video is something, and there's the third video is even shorter, but that's fine. Okay, hello, am I there?
Yes, sir.
Okay. Yeah, good. So no, I will go slowly. Don't worry. I have decided to kind of I will not be covering whatever has been written in the web page at least next week. I will go slowly, but mm, yeah. So don't worry about it. Uh, so just let me know if you guys want some other. I mean, not a class. Okay. I mean, this online sessions is mostly for sorting out doubts. So if you guys want one more session for sorting out doubts, okay, and let us know, and we will accordingly organize. Yeah, I will.
So are we will we get assignments every week? Like
No,
what is
no, no,
the
no, 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 no. You will get every 2 weeks.
so
Yeah.
so my suggestion would be like if the weeks in which we are not getting assignments, in those weekends we can have doubt clearing plus problem solving classes. Like that would help us a lot. Because let's say this weekend can be utilized for assimilating all that has been taught and
Okay.
then working on the assignments.
Okay.
So that
Sure.
will be my suggestion. I don't know. Like let's say what others have to say. I don't know. So,
Sure, no problem. I mean, that's perfectly fine with me. Yeah, again, I mean, so let me put it this way, okay? So there will be no class as such. By default, there will be no class this Saturday. But if there are some people who want some more discussions on whatever has been done or have struggling with some notions and all, please let us know by tonight so that one of our TAs can.
Sir, we did not hear the last line.
Oh, you
The
can,
audio was cut off.
now you can hear.
Yes, yes.
Okay, no, I think that so let's say that we will not have a class on Saturday, but if there are some people who are interested in sorting out some clarifications about whatever concepts has been taught in class till now, okay, please let us know ideally by tonight, and then maybe on Saturday, the one of the TAs can kind of have some kind of doubt clearing session. It will not at all be mandatory for people. We may not be doing anything new. Okay, just in case these notions and all whatever has been told till now, you guys need a clarification, you can the TAs will help you. Okay, so but if you are interested, please let us know. I mean, else we will assume that there is nobody interested and we will not be conducting this. Does it make sense?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So in that case, I will see you guys on Tuesday, and yeah. Again, just to get that in the notes that has been given, I don't expect you guys to read all of it, okay? But for the next week, one thing that I really need you guys to do is these asymptotic notations part. Okay, chapter 2 of the notes. Even if you cannot solve the exercises in that note, some of the exercises in notes are very hard, that's still fine. But the concepts and the definitions, you should really be very accustomed to. Because I will be using that notation left and right. Okay. I can spend some time on Tuesday on that also, but I want you guys to at least read it up and come. Fine? Yeah.
Sir, I wanted to ask, are pseudocodes necessary in the assignment? Like, just algorithm won't work. Like, we have to write the steps for the like proper code, because algorithms, I mean, the more or less they are the steps. So, like, do we have to write the pseudocodes as well?
I mean, pseudocode is not a code. Pseudocode is a set of steps.
Yeah, no, but like in algorithm, we are anyway explaining what we are doing.
No,
so,
I mean,
like,
I think for this particular assignment, okay, as I told you, except for the 6th problem, I want you guys to write formally steps. I don't want to see one paragraph of explanation in English. Okay.
Okay.
I mean, for this assignment particularly. I mean, because I mean, you get. I mean, this is very easy. The pseudocode here is very easy. Okay, so writing it will be kind of easy. Okay, so it's not too hard. If you have the algorithm, writing it up will just take you 2 minutes to write it. Okay, so I insist that you write pseudocodes for this project at least, this assignment at least, because it's a very common tendency to go on writing. Yeah, for the 6th problem, I'm not insisting on that.
So, but pseudocodes in the way you gave in the video are fine, right?
Yeah. Even less than that is fine. I want a step. If you can write even step 1, step 2, step 3, step 4, I am perfectly fine. Okay, that is also a pseudocode. I don't want a code. I'm not going to run it on a program. I'm not going to code it up in C. But I don't want a half a page explanation in English. You can give that extra also. Okay, half a page explanation of why the algorithm is correct and wrong. But the algorithm should have some amount of a formal structure to it. Some steps. Okay.
Okay.
So, can we write like Python code rather than pseudocode? because it's almost similar to you.
Yeah, go ahead.
Python is
I mean, you give me something more than what I asked. I have no problem.
okay.
Okay, so if there's no more questions, it's a long session. Okay, so let me stop here now. Okay.